Welcome to The Explainer. All right, let's just jump right in, because today we're tackling one of the most mind-bending, profound, and just downright strange concepts in all of science, quantum entanglement.
And you really have to start with this famous phrase. It was coined by Albert Einstein, the very guy whose intuition was so shaken by this idea that he spent decades trying to prove it, well, that it couldn't be the whole story. Spooky action at a distance. I mean, it just perfectly captures the mystery we're about to get into.
So, what was it? Why did this idea bother the architect of relativity so much? Well, to get to the heart of his whole spooky puzzle, we first got to wrap our heads around what entanglement actually is. So at its core, entanglement means that two or more particles can get so linked up that they basically act like a single thing. It's like their individual identities just merge into this one shared reality. And the crazy part? This connection holds. It doesn't matter if they're right next to each other or separated by billions of light years. Now, this whole weirdness is possible because of two, let's call them, foundational rules of the quantum world. First up, you've got superposition. This means a particle, say an electron, isn't just spin up or spin down, it's actually both at the exact same time. Then there's the second rule, measurement. The moment you look at that particle, you don't just see what it's doing, you actually force it to pick a state. It's wild. This is what we call wave function collapse.
Okay, I get it. This sounds deeply weird, totally abstract. So let's try a classic analogy to, bring this whole idea back down to earth a bit.
Okay, imagine you have a pair of gloves. You put one in box A and the other in box B, without looking. Then you mail box B to the other side of the galaxy. When you finally open box A and see you've got the left-handed glove, you instantly know, no doubt about it, that box B has the right-handed one. It's just simple correlation. Makes sense, right?
Well, here's the thing. That analogy feels right, it's intuitive, but it's also completely misleading. It totally misses the real spookiness that had Einstein so puzzled. The truth about entanglement is way, way stranger than a simple pair of gloves.
And here's the absolute crucial point. With the gloves, they always had a set-handedness. The left glove was always the left glove, right? Looking at it just revealed a fact that was already there. But with entangled particles, their properties, like their spin, are genuinely up in the air, completely undefined until the exact moment one is measured. So your act of looking doesn't just reveal a reality, it literally creates it.
And that idea, that reality isn't really real until we look at it, well, that sparked one of the biggest scientific debates in history. This was a battle for the very nature of reality itself.
So back in 1935, Einstein and his colleagues, Podolsky and Rosen, they put out this famous paper. We call it the EPR paradox. Now, they weren't saying quantum mechanics was wrong exactly. What they argued was that it had to be, well, incomplete, that it was missing something fundamental about a deeper, more common-sense reality.
Their whole argument was based on two ideas that, frankly, feel like common sense. The first is realism. The moon is still there even when you're not looking at it. The second is locality. What I do right here can't instantly affect something happening across the universe. Put them together and you get this worldview called local realism.
So to try and fix this incompleteness in the theory, they came up with this idea of hidden variables. Think of it like this. Maybe the particles have some secret instructions written down from the very beginning that tell them how to behave when measured. That would explain their perfect connection without any spooky action. And for decades, that's where it stayed, is this huge philosophical debate. It was basically just a back and forth between the giants of physics. But then a physicist named John Bell came along and figured out a way to stop arguing and actually test it. He figured out how to put reality itself on trial.
What John Bell did in 1964 was nothing short of genius. He created what's called Bell's theorem. He basically transformed this whole philosophical debate into testable physics. He figured out a mathematical limit on just how correlated particles could be if Einstein's local realism was true.
So the test was simple. Einstein's worldview predicted that the correlations between these particles had to obey a strict limit, what we now call Bell's inequality. But quantum mechanics predicted something totally different, that the correlations would be much stronger, that they would actually violate Bell's inequality. It was a clear-cut showdown. So, what happened when physicists finally ran the experiments? The time for debate was over. It was time to just ask nature directly.
And this wasn't just one single experiment. It was a decades-long investigation. It kicked off in 1972 with Clauser and Friedman. Then in '82, Alain Aspect's experiments closed a huge loophole. It all led up to 2015 with these incredible loophole-free tests that basically provided the definitive proof. And for all this work, Aspect, Clauser, and Zillinger were awarded the Nobel Prize in 2022. I mean, that's how big a deal this was.
And the evidence was just overwhelming. Time and time again, the experimental results smashed right through Bell's inequality and lined up perfectly with what quantum mechanics predicted. The verdict was in.
The verdict of reality is in, and it turns out to be stranger than our classical intuition could have ever imagined. Einstein's common-sense view of the universe, well, that's not the universe we live in. Reality is, in fact, spooky.
So why does this matter? I mean, beyond being a really cool physics puzzle. Well, because this spooky feature of reality isn't just a curiosity anymore. It's actually being harnessed as a powerful technological resource. It's the engine behind the next big thing. This entangled engine is driving three huge fields. In computing, it creates this vast computational space that can solve problems that are impossible for today's computers. In communication, it's the key to creating secure key exchanges that are guaranteed to be safe from eavesdroppers. And in sensing, it helps us build detectors that are so precise they can surpass any classical limits.
Yeah, we're talking about harnessing this connection for some amazing things, like creating unbreakable cryptographic codes, building computers that can run algorithms like Shor's to solve massive problems, and developing hypersensitive detectors like LIGO that can actually sense gravitational waves. This isn't just theory, this is the foundation for a future quantum internet.
Okay, but let's address the big question. Does this mean we can communicate faster than light? The answer, and this is important, is a definite no. Even though you know the state of your partner particle instantly, you can't actually control the outcome to send a message. The result you get is random. So causality is safe. You're not breaking the cosmic speed limit. So, at the end of the day, what if the universe isn't really made of separate individual things at all? What if, at its most fundamental level, it's all about connections? Entanglement has totally changed the game, forcing us to ask, what else about reality have we just not seen yet?